Okay, you guys, so here's the story. We get to do error. This is the last section in this topic of Taylor polynomials, and it's a little different than alternating series, a little bit more complicated because you have to maximize derivatives. So all that stuff we did first quarter, where we found maximum values and minimum values and all that stuff, is very important here. This is one of the many reasons why we do it, in addition to the fact that it is fun. So this whole section talks about how to know how close you are if you stop at a particular term to what we're considering to be the real sum. So two things that you want to know about is that the approximation is usually better where it's close to A, in this case we're using C for center, than values far from C. And I think in your notes I had corrected that, maybe not. And then the higher the degree, the better, right? So that if I go out to the 6th, 8th, 10th term, that's better than just going out to the 3rd. And what this says is the error, so this is how to find a Taylor, which you already know. To find the error, so this guy means error. This says the maximum value of the next derivative. So the max, because remember we're doing derivatives for these, value of the next derivative. And in most notes they call this z because you don't want to confuse it with the center. It's not the center. It's just an x value that produced the maximum. Once you have that, whatever that next term is, that's the factorial of the next term. And you'll understand what I'm talking about when we do some examples. And then this is x minus the center, so we called it c, you can call it a, to the next term. So this n plus 1 plays a double part. It's part of the factorial and it's also part of the power. So for example, let's just take a really quick example. Let's pretend you have a function. So if you have f of x equals, I don't know, x to the 5/2. And I want to use the Taylor series to approximate, so approximate, using it to do like 3.4 to the 5/2. Okay, that's not a nice number. And so we're going to have to figure out, well, where do I want the center? Now 3.4 isn't too far away from a center of 3. So let's say I have a center of 3. So we're only 0.4 away. Then using that center of 3, you would set it up like this. You would say it would be 4.3, I said that backwards, 3.4 minus 3 to whatever that power is. So it would depend on where we're stopping. And then you've got the maximum for n plus 1, which is really all that is, over n plus 1 factorial. And we put that into absolute values because, as you know, error could be greater or smaller than that. It could be within that. So you could have an x within the plus or minus value. So that's why we have the absolute value. So that's probably still not very elucidative to you. Illustrative, whatever the word is. Okay. So oh my goodness, I actually picked the same one that we're doing. Okay, this is just a reminder of something that you still don't probably understand. Okay, so Taylor series, this is a Taylor series. This time my center, so I could say C or A, whatever you're using, is at 4. So I'm going to have to actually write this out. I'm going to have f of x, and then f prime of x, and then f double prime, and f triple prime. Now we're only going to have to go out to triple prime because it tells me 3rd degree. So this means 3rd degree. So the triple prime is going to match with a power of 3. So I'm going to do it in general. So I've got x to the 5/2 And then I've got 5 halves, x to the 3 halves. And then I've got 5 halves, and that's supposed to be a 3. It's kind of hard to read that. X to the 1 half. And then I've got, and did I do something strange? I feel like I did. 3 halves. Yes. So when I'm multiplying these, this should be 5 over 4, right? Because I'm multiplying down. In fact, 15 over 4. Where did I get that from? I don't know. So we've got x to the 5 halves. Bring down the 5 halves, subtract 1. Bring down the 3 halves, so 5 times 3 is 15, 2 times 2 is 4, x to the 1 half. And then I'm going to bring this guy down one more time, and I'm going to have 15 over 16. And I still feel like I did something wrong. I'm just teasing. 15 over 8. Holy cow. 15 over 8. X. And this time I've got the negative 1 half. Okay. And I'm plugging in 4. So I'm saying 4 to the 5 halves. Well, that's square root of 4, which is 2. 2 to the 5th is 32. So you're evaluating each of these. I'm putting in 4. I'll just write down what I got. I got 20. This one I got 15 over 2. This one, when I stuck a 4 in there, that's where I got the 15 over 16 from. I was thinking about plugging it in already. Okay. So my Taylor for this starts with the first, so it's 32 plus 20 x minus 4 to the first over 1 factorial plus, and why did I get, oh, I did get 2. So this guy is 20, and then I've got 15 over 2, got the x minus 4 squared over 2 factorial. And then I got to go one more. So I've got 15 over 16, x minus 4, cubed over that times 3 factorial. So I've gone out to the third term. I've constructed the Taylor polynomial. If they didn't ask me anything else, I'd be done. This is saying, now use that to figure out 5 to the 5 halves. So all I'm going to do, so this is my Taylor polynomial. I would say T3, it means third degree Taylor. Even though I've got 4 terms, it's a third degree Taylor, for x to the 5 halves. So when I'm doing the polynomial for 5 to the 5 halves, that means I just substitute 5 in. So I still have 32. Now if I substitute a 5 into all of these, I'm just going to get 1, right? So 5 minus 4. So I'm just going to be writing the coefficients and the factorials. So this is going to be 15 over, what is it? I don't know, 15 over something exciting. 2 times 2 factorial. And then I'm going to have 15 over 16 times 3 factorial. Okay, so stopping at that term. And that's going to give you approximately 55.90625. Now, if you use a calculator, which is just doing this to more, with the center perhaps closer and to a larger degree, you get 55.901,69944. Which is pretty darn good. Check this out. We're good until we get to the third decimal place, and we only used 3. I just realized I wrote T5. I think I was thinking about putting 5 in. Silly me. Okay, so that's T3. All right, now it wants the error. I want to know the error in this interval. Sometimes they'll give you the interval, sometimes they won't give you the interval. In this case, I need to know, or I need to know how far away my value is from the center. So what I need to do is maximize the next derivative. So remember, up here, my third derivative was 15 over 8 x to the negative 1/2. So f triple prime was 15 over 8 x to the negative 1/2. And I just want to run back up and make sure I wrote that correctly. Otherwise, we're going to be misfiring. Okay, that's looking good. I want the maximum of this. I want the maximum of f4, which is the fourth derivative. So f4 is negative 15 over 16 x to the negative 3/2. But remember, to maximize it, you have to take its derivative, right? If I want a maximum of something, I need to take the derivative and find critical numbers. So we're going to take the derivative. And this is so I know what to plug into my formula. So now I've got 45 over 32 x to the negative 5/2. I'm going to find critical numbers for this. And we're looking for the maximum value on that interval. Now the only critical number would be 0, right? Because that's going to be x to the 5/2 on the bottom of the fraction. But my interval is only on 2, 6. So 0 is not included. It's not relevant for this. So I check the endpoints only. So I'm going to check 2 because it's an endpoint. And I'm going to check 6 because it's an endpoint. Remember, when I did this initially, I used to make a chart and I would say, what are my x values that I'm using? Why am I using it? And then what is the value? And the value is plugged back into the original function, right? So this 2, when I am looking for the value, I don't plug it back into the derivative. I'm plugging it back into the fourth derivative. I just said that backwards, didn't I? No, I didn't. That's correct. I'm plugging it into there. Okay, so if I want the value for this one, I am going to get negative, and you can put this in your calculator if you don't believe me, 0.33134. The next one you get negative 0.06378. And we're considering these in absolute values because remember, the formula is an absolute value formula. So I want the biggest one. So pick the biggest. Well, clearly, if I am looking at absolute values, 0.33134 is the largest. So that's what I use in my formula. So let me just rewrite the formula really quickly since I'm kind of down on the page. My error is within. Now there's an equal sign in there too. The next derivative's maximum, n plus 1 z over n plus 1 factorial times x minus c to the n minus 1. So we can fill all of that stuff in. So we are on the fourth, right? So n plus 1 is right here. N plus 1 is 4 because that was 1 past 3. So fn plus 1z, this is the maximum that we just found. So my error is going to be within that maximum, so 0.33134 over 4 factorial. Now my interval, remember I'm using 5, so it's 5 minus 4 to the 4th power. So the idea is we want the error to be as big as possible so we can be absolutely assured. So we want this number we want the maximum because I want to make sure my error has to be within, I'm forcing it to be within a certain number. And if I work that out, I get 0.0138,106. So my error is less than that, plus or minus that. Okay, so it's a complicated thing when you first see it. It's sort of obtuse. So what we did again is we looked at a Taylor series for x to the 5 halves, wrote it out, stuck in 5 because we were looking for 5 to the 5 halves, came up with a value, came up with our value, the calculator value, and then we looked at how close is it. So this says you got to take the maximum of the next derivative. So we stopped on the third term, right? The third derivative was the last thing that we used. It says maximize the next derivative. So you got to find the next derivative. If I want to maximize something, I have to find its critical numbers. So I have to differentiate it, which is what this is. Find the critical numbers. So this is going to be an x on the bottom of a fraction. And remember, critical numbers are where the denominator is equal to 0 or where the derivative itself is equal to 0. So we picked 0, but 0 is over here somewhere, right? If I continued my number line. My interval is 2 to 6. So because of that, I cannot use 0. I don't want to use 0. So I pick the endpoints, because remember maximums can occur at the endpoints or at critical numbers, of which for this one is 0, and that doesn't matter. So I checked out 2, I checked out 6. The value for 2 has an absolute value that's larger than 6, so we pick that, put it up here. That's what this means. This means give me that maximum value, 0.33134. Now the one that we were maximizing was the fourth. We maximized the fourth. So that's why this is 4 factorial, and that's why this is to the 4th power. Okay, just a baby recap. So let's look at another example. This page gives you a rundown on exactly what I said. So the LaGrange error bound, or LaGrange, however you want to say it. Okay. So let's look at one. This is a little bit simpler, I think, than the one we just did. And it'll help perhaps solidify what we were just doing. So it says, using Taylor's theorem, we can write sine x. Now, of course, you have this committed to memory by now. X to the 3rd over 3 factorial. And we're going to estimate accuracy by using a certain amount of terms. X to the 5th over 5 factorial minus x to the 7th over 7 factorial plus blah, blah. Don't really care about the general term for this because I'm actually just trying to find the error. So P3 is the polynomial, or I could say this is T3. This is the 3rd degree Taylor series for sine. Well, the 3rd degree cuts off right here. So really we're just using the first 2 terms. And I'm using the value 0.1. So I'm going to have 0.1 plus 0.1 cubed over 3 factorial. Okay, and if I work that out, that value is 0.09909998, and then 3's repeating. I think there are 5 of them. Okay, so we can find the accuracy of doing that by finding the LaGrange form of the remainder. So we stopped at 3. I need to maximize 4. So I'm going to maximize. So this means the maximum value of 4th derivative. I'm going to be dividing that by 4 factorial. My center is 0. So I'm going to have 0.1 minus 0 to the 4th. All of that is in absolute values. This is my error, maximum error in stopping at the third degree. Okay, so f4 of z. Now, when you're dealing with sine or cosine, you want the worst case scenario. I want to know biggest value for sine, okay? Because my fourth derivative, so remember, we're starting with sine x, and this was not explicit in this example. Its derivative is cosine. Its derivative is negative sine. Its derivative is negative cosine. Its derivative is sine. So this is f prime, f double prime, f triple prime. That's where we stopped, right? That gave us this value right up here. We need to maximize this one. This is f4. Sometimes I write Roman numerals, sometimes I just write the number 4. We need the maximum of this. One, two, three, 4. So I'm really maximizing cosine. So I want the fourth derivative. I want to maximize sine. So that's my fourth one. I'm sorry, I said that wrong. Maximize this. And to do it, I have to find critical numbers. So maybe I will change this to critical numbers. We want critical numbers and endpoints for this. So find critical numbers or use the endpoints. The endpoints being 0.1 and 0. Now for sine and cosine, you want it as bad as possible, right? I want the biggest possible error because I want to contain the error within a certain amount. So for these, we know maximums for sine and cosine. The very, very biggest value that sine or cosine can take on is 1. So I'm going to use 1 as my maximum. Remember, this is the maximum of the next derivative. Okay. So, and this is what it's saying. It may never actually be 1 on that interval, but that's the worst case scenario for this. So my error is going to be 1 over 4 factorial. And then my center, 0.1 minus 0, this is Maclaurin, to the 4th. Absolute value of that. And if I do that, I get this crazy small error. I think there are 5 zeros. Your calculator will pop out scientific notation for this. It's not wild about putting zeros in there. Okay, so we can conclude that T3 of 0.1 is less than sine of 0.1 is less than point. So this just means my error is within that value. That is the biggest possible. Oh, did I do that right? Yeah, 416,666, the devil number. So that means that's my maximum error, and all I did was stop at x cubed. Is that not crazy? Taylor polynomials are very, very powerful. And the other reason why this is so good is that center is at 0. I'm only 0.1 radians away. And remember, these are radians. We're in radian land. We're not in physics. Okay, let's look at another fun example. So this time, I've got e to the negative 0.1. And the beautiful thing for this is that we're looking for a Maclaurin, right? The reason that's important is that my center is 0. So again, 0.1, negative 0.1 is left of center. It's 0.1 away. So let's construct the Taylor polynomial. This again is something you have committed to memory. So you got 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th. My question is, where do I stop? I want to know what happens if I carry it out to 4 terms. So I'm going to write more than 4 here. Okay, so this I didn't have to actually construct. I want to know how accurate is it if I lop off these last two terms and everybody to the right of it and just use this fourth degree Taylor. I want to know how close am I in case I need to be closer. I might need to be closer. Okay, so we do have to think about what the derivatives were that generated this because we're going to need to maximize them. So let's think about how those came about. So let's see. So we're looking at it in general. So I've got e to the x, and then its derivative, of course, is also e to the x, e to the x. This is kind of boring. So that's 1, 2, 3, 4. We're maximizing e to the x. So that's 4. We're maximizing this, a little bit boring, which means we need its derivative. So this is also e to the x. So this is f. This is f prime. This is f double prime. F prime, f double prime, f triple prime. I didn't go far enough. Let me get rid of this. That's why I like to write these out. F, that's my fourth derivative, which matches with my fourth term. So I'm maximizing that. And for that, I need to go to the next one. Now this is boring, right? Because e to the x is its own derivative. So I need to know what e to the negative 0.1 is. So remember, my interval is between 0 and negative 0.1. So negative 0.1 to 0. E to the x is an increasing function. So I already know, right? So here's e to the x. Here's negative 0.1. Here is 0. Clearly, it's going to have to be bigger at the endpoint, right? This right endpoint is going to create a bigger value. It's an increasing function. So I can either bust out the e to the negative 0.1, but that's what I'm trying to find. So I'm going to just use the endpoint, e to the 0, which we all know is 1. That's my maximum. Okay, that's going to produce my maximum value. Now, if it were an e, then I'd have to plug this in. So I'm maximizing x to the fourth, or sorry, f4, the fourth derivative. So I would plug that back in here. So we're plugging 0 in there. And we're getting the 0 from here. So this is the max of f4 because of the increasing function. That's because of this. Okay. So then I'm set up, right? It says maximize the fourth. Actually, maximize the fifth. I keep saying it wrong. It's because e to the x is the same all the way through. So if I'm maximizing that, I went out to the next derivative. Again, kind of boring. Let me change this. Bam. So we went to the fourth, we're going to the fifth, and then maximizing that. Okay. So this is f5. To do that, I needed its derivative. Okay. Fortunately, everything is the same because we're just dealing with e to the x. So let's find the error. We went out to the fifth, so this is going to be 1, right, because this value is 1. Over, we went out to the fifth, so I got 5 factorial. That was the n plus 1 term. So this is n plus 1 is the fifth. Then I've got 0.1 minus 0 to the fifth power. Figure that out. You get 0.1, 2, 3, 4, 5, 6, 7 zeros. And then you get an 833. So the error is within that much of the real sum. So let me write that. So the value for e to the 0.1 will be within that much of the real sum if we added forever, if you stop at the fourth degree. That is crazy cool. So we have this itty teeny weeny bitty error by stopping relatively short. We didn't go very far. So you can imagine how that increases as far as the accuracy. Okay, so I hope that was clear. Let me just run through it one more time just so you hear it again. We wanted the fourth Maclaurin polynomial. So I went 1, 2, 3, 4. It was 5 terms because this guy is x to the fourth. And generally, if I were doing this, I would actually write out derivatives. These all happen to be the same, which is why it can be confusing for this example. I have f, f prime, f double prime, f triple prime, fourth derivative. Because we're stopping on the fourth, we maximize the fifth. In order to maximize the fifth, you have to have critical numbers. Well, critical numbers say take its derivative. So its derivative is still e to the x, and by inspection and by the fact that I know my e to the x graph, which is right here, negative 0.1, which is this guy, versus 0, well, 0 is going to produce the bigger number, clearly, because this is an increasing function, and we know e to the 0 is 1. So I'm going to use 1, and that's going to be up here. That's my maximum. I stopped on the fifth. This is the one that I maximized, which is why this is 5. It's why this is 5. The interesting value, what I was trying to find was 0.1. It's Maclaurin, so you subtract the center, which happens to be 0. Work all of this stuff out, and you wind up with tiny error. So if I stop up here at degree 4, I get itty bitty error. So imagine what would happen if we kept on going, which is really what your calculator does. It just keeps on going because you can program it. All right, example 9. We only have 2 left, which is pretty nice. Okay, so this one is a little bit more complicated only because I have to come up with cosine of 2x plus pi over 6. And really, all I need to know, because we keep doing fourth. No, we don't. This is good. We're doing a third degree Taylor, so now you can see a slight difference. So I'm trying to prove this is how the AP will tell you error. F of 1/3 is the real value when x is equal to 1/3 in this function. This P of 1/3, we also say T of 1/3, so it's the same as T 1/3, means I've stopped somewhere. My question is, how close would I be if I stopped at 1/3? So that's why the difference between the real value and stopping somewhere, they want to limit it to 0.001. Okay, so if I found the real value versus stopping, that difference is the error. I want to make sure it's less than 0.001. So the question is, where do I stop? Or actually, in this case, it says the third degree Taylor at 0. We want to use the LaGrange error bound to find the error and make sure it's less than 0.001. Okay. And in this case, they're saying, show me that the third degree Taylor is going to be smaller in error than 0.001. So I hope that's clear. All right, so here we go. I need to find derivatives, right? So I know my f of x, and I got my f prime. So you can't just say, it's not like e to the x where everything's the same. F triple prime. And this is my third degree. This is where I would stop. I'm going to be maximizing this one, which means I need to go out to find critical numbers for the fifth, and then plug those back into the fourth. So let's find the derivatives first, because we need to know what that value is to know the maximum. So f of x, and I'm just going to do these in general, f of x was cosine 2x plus pi over 6. Its derivative is negative 2 sine 2x. So don't forget the, oh my goodness, I don't remember what it's called, chain rule. Derivative of sine is cosine, so I'm going to have negative 4 cosine 2x plus pi over 6. Derivative of cosine is negative sine, so this is going to pop out positive 8 sine 2x plus pi over 6. Now, that's where I'm stopping. That's my stopping point, which means I need to go to the next one and I need the maximum of this. So find the maximum. And for that, I'm going to need to do the next one. So the maximum for the next derivative is going to be, so sine's derivative is cosine, so it's going to be 16 cosine 2x plus pi over 6. But that's what I'm maximizing, so I need to come down here and find critical numbers. So cosine's derivative is negative sine, so this will be negative 32 sine 2x plus pi over 6. Just taking a bunch of derivatives. This I need to find critical numbers. So the maximum of that, now this is a Maclaurin series because x is equal to 0. So I know my center is 0. And the questionable term, or the questionable value, is 1/3. So if I were to write an interval for this, this would be 0 and this would be 1/3. And I need to know which of those gives my maximum value. So if I do cosine of 0, now again, this is cosine, sine. I don't really have to do this. If I didn't have cosine or sine, I'd have to figure out which of these two is bigger and whatever critical number's in there. But in this case, I can use either, you can think of it as cosine of 0, or worst case scenario for sine or cosine is the max is 1. So that's a good rule of thumb. Sine and cosine, you kind of already know the max. So in this case though, if I put a 1 back in here, so the maximum is 1. It occurs at 0, right? So I shouldn't say maximum equals. Maximum is going to occur at 0. I need a pen. And if I take 0 and I plug that back in, the height of this is my amplitude of the graph. So the amplitude of the graph, the worst case scenario in this case, is that my max is 16. Okay, so you really have to think about what you're plugging it into. You can't just automatically say 1 unless you're at the center and you got 0, so like this one we could do that. But in this case, my function was not just cosine of something, it was cosine of stuff in here, which we had to do chain rule for. So here it is. I'm going to say the error is less than the absolute value of 16, which is my maximum, over, now we stopped at the 4th, right? Or I should say we stopped at the 3rd, which meant we had to maximize the 4th. So n plus 1 is 4. So this is going to be 4 factorial. My center is 0, so I've got 1/3 minus 0 to the 4th. I need to figure this out. If I do so, now this was on a non-calculator part. Can you imagine? This is on a non-calculator part of the AP. It was so similar to this, this might have actually been the question, though I don't think it was, but it was very similar. You had to do this by hand. You got 2 over 243. And you would need to show that that's less than 1 over 100. Now, if you had a calculator, you could work this out and say this is 0.008. 23 is certainly less than 0.01. So that's it. But I remember on that particular AP question, you would have to know that the value of this fraction is smaller than 1 over 100. Okay, so this one is a proof. They give you everything. They don't tell you to find the error. They give you an error and they say, where do you stop? What is the maximum error in stopping there? So you have to recognize that 1/3 is the value that we're interested in. It's at 0, so 0 minus 1/3, or 1/3 minus 0. In this case, it doesn't make any difference because I'm going to be taking absolute values. All right, example last. This is it. Actually, I have another itty-bitty example that I just want to show you because sometimes they give it to you as a graph. I'll do that on a different page. All right, so this says you've got a function. It has derivatives on all orders for all real numbers. Important thing, because if it doesn't have a derivative, we're done. We got a 3rd degree Taylor. It's about x equals -2. So this is my center. So c equals -2. And they tell you the polynomial. They say, here it is. Here's my 3rd degree poly. They tell me the 4th derivative gives you this for all x. So they're telling you, you've done f, you've done f prime, you've done f double prime, you've done f triple prime. You're stopping at triple prime. And they're saying that in doing this, you get f4. When you maximize that, so this is maximized, you didn't have to do, excuse me, you didn't have to do any work for this, right? Maximum, maximize. They told you that maximum value. So this is the maximum of f4. So that is the maximum. And in order to do that, you had to go to f5, but of course we don't have the function, which is what AP loves to do, is not give you a function and make you say, do you really understand that? So this maximum is 25. It's within 25. So less than or equal to 25. So that's your top number. My center is -2. And they're asking me to find the error approximation for f of -1.6. So it's -1.6 minus -2. So your maximum is 25. Underneath, I've got 4 factorial, because remember, we're stopping here. We're maximizing this one, because we stopped here. Maximize the next one, which means I have to find critical numbers of the 5th. But we don't need to do any of that because they told me the maximum. So 25 over 4 factorial, -1.6 minus -0.2. And if you work that out, and again, this one is possible to do without a calculator. It's a little bit intense, but you get 25 over 24. If you work this out, it's 0.4. And I forgot my power. This is to the 4th. Okay, with a calculator, not too bad. It's 0.02667. So that's my error for whatever this thing is in stopping at the next term. So okay. Okay. So here we go. I had one last thing I just wanted to show you because this also appeared on an AP question once. And I'm just completely making this part up. Oh dear, that's terrible. Okay. Let me see if I can draw a real typograph. I'll just do lines. Okay, so if I've got, let's say I've got a graph, and let's say I've got a couple of numbers on it. Okay. So, I don't know. Something like that. I don't know. And let's say this is your center. And let's say you're trying to approximate the error in being 0.1 away from the center. So we're 2.9 to 3. Scale is way off. Okay. And maybe I'll move this up just a little bit so it's more convincing. Okay. And I know that this is, and again, I'm totally making this up just because I know this type of question will come to bite you, and bite you hard. Okay. They will tell you something like this. They'll say, find the error for a 6th degree polynomial centered at 3, given that this is the graph of T7. So they may not say T7, they may say P7 of X, T7 of X. So you're looking at centered at 3, the error for a 6th degree polynomial centered at 3 to approximate, I didn't finish my sentence, approximate f of 2.9. Okay. Actual question on the AP, very similar to this. So graphically, and they didn't even give you the numbers on the graph, they expected you to approximate these. And they were a little bit better than this, but not by much. Let me get rid of that. Or just move it up. So if that's 5 and this is 12, I was trying to make them look good, but they're not that good. Okay. So this is T7. Well, that's a good thing because I need the maximum of T7 to know how to stop at a 6th degree. So in this case, this is going to be, now remember the error, be nice if I wrote error, R. It's actually one of the ways that you write it, but I'd rather just write words. So error will be within the max of the next derivative. So this would be max of 7th derivative. Yeah, maximum of the 7th derivative. Let me think. Over, in this case, it would be 7 factorial. And you might say, why are you working with 7? This will be 2.9 minus 3, because my center is at 3. Well, I'm using the 7th because it said stop at the 6th. This is the 7th, the maximum value of which on this interval occurs right here. So instead of writing maximum of 7th, of course, I'm going to write 12 over 7 factorial within 2.9 minus 3. And then you work that out. Now, when I did it in my notes, I think I did a 5th degree and a 6th degree, but you work that out and you get a tiny number, which is the error. So here they just gave you a graph. It didn't seem like they gave you enough, right? because you didn't know what the polynomial was. You just knew it was 6th degree. You knew its center, and you had a graph of T7. But T7 is what I want to maximize. Now, if I had a function, I would have to find T8 and find the critical numbers. But I don't have a function. All I have is the graph. But the graph is T7, and I'm looking for the maximum value. So from that graph, you would pick the left endpoint, which appears to be 12, because I just made that up. The maximum of the seventh derivative from the graph is 12. It is 7, that's n plus 1, so we stopped at the 6, so 6 plus 1 is 7. And I did not write 7 up here, which was an omission on my part, to the 7th. That'll give you a teeny, teeny, tiny number. Okay, so that's all I can think of for Taylor. When you are doing your homework, it's going to ask you for error. I crossed this out, so because I used to teach it a different way, and it used a chart and it was kind of obtuse, and I thought it was easier just to be straight up with it. So have fun with the homework. I'm going to be posting answers, and then we're going to have a homework party tomorrow, or when I see you again, because there's a lot of homework we haven't gone over. Okay, so have a fun rest of your weekend. Be good, and I will see you next week.